Greetings to everyone.
Well, thank you, Fabien. This is Mark Unkefer, and welcome to the monthly Fiber Optic Sensing Association webinar. This month we have Fabien Ravet of Omnisens, and his webinar is on transportation infrastructure geohazards risk monitoring. So we're going to hear about fiber optic sensing in some very rugged environments and where other sensors would not be available. So thank you. Just a bit of housekeeping. We will have an opportunity to do questions at the end of the presentation, and that will be done with the box on your right and can be handled by text. Also, we are recording this presentation, and it will be available on the FOSA website in another day or two. Fabien, we look forward to hearing your presentation. Thank you very much.
Thank you very much, Mark. And I know that there are people from everywhere in the world, so I don't know if I have to say good morning, good afternoon, good evening, or I can say everything else at once. Well, I'm very glad to be here to share a little bit of our experience in our work about optical fiber sensors and actually optical fiber distributed sensors on transport infrastructure geohazard monitoring. So I will start the presentation by a quick introduction. Well, reminding a little bit of what geohazards are. It will be a bit a simplified approach, but to put everything in the context, I'll also introduce how these geohazards can affect transportation infrastructures, as well as how optical fibers can help protect them. Then we'll enter into the real body of the presentation, which is about the technology. And as a physicist, this is the part that I like the most. In all my presentation is talking a little bit of physics and scattering and optical stuff. I'm a fiber optic geek, and I'll stay up to the end of my life. Then we'll go over the geohazards themselves and see how an optical fiber can help us detect them, and we'll see what's the signature of a geohazard in a distributed optical fiber sensing system. We will see then how an optical fiber can be installed along a transportation infrastructure. I don't have the pretension to be very comprehensive, but at least to give you some guidelines or basic ideas of what can be done. And well, we will then talk a little bit, we'll say a few words about what a geotechnical monitoring system is and what it must have. And we'll see how it has been implemented in a real case, in a real world case, and operating since 2010. And of course, I will be ending my presentation by some concluding remarks. Well, so let's start, and let's do some introduction. Well, so when we talk about transportation infrastructures, it can be pipeline, it can be highways, railways, let's say a linear structure. And what is good with linear structures is that they can fit with optical fiber communication cables. And when we can install an optical fiber communication cable, it means that we can also implement optical fiber sensors. Why? Just because optical fiber sensors, including telecom fibers, can be used for sensing. You can turn these optical fibers into strain sensors, strain gauges, into temperature sensors or thermocouples or thermometers, and even into microphones to detect vibrations. And what is very interesting and very nice with that kind of approach is that you can achieve distributed measurements. I will elaborate a little bit more about distributed measurements later. And well, what is very important to know for those of you that are new with optical fiber sensing is that, well, we are not as old as optical fiber communication, but we have a system implemented for at least 16 years now, and in some cases even for a longer time. So this is not such a new technology. Well, now talking about geohazards, well, we have, and that's the most known, the most dramatic usually in the consequences, we have landslides, rockfalls. So just a mass movement of material that can be lethal. Then another kind of ground movement or geohazard is subsidence, soil settlement. So this usually happens where we are in Arctic environments where the permafrost can melt and provoke a settlement of the ground, or in karstic terrain where you may have the formation of cavities and skin holes, which will pull back a pipeline, for instance, or even crack a road, crack a pipeline railway track. A pipeline railway track, yes. And finally, the last one that we are, let's say, considering as in our classification is soil erosion. So soil erosion can come from water streams, water flows, but also from wind, like in desert, where we have dune migration. So those three geohazards are the categories we are considering in all the discussion. And well, the geohazards can be, or they are very depending on the type of terrain, the nature of the terrain, and on the climatic conditions. So it's kind of understandable that some regions in the world are more prone to geohazards than others. And for instance, if you have a pipeline crossing a mountain range in a tropical region, the probability of having a landslide is very high. So this is all the consideration that we must take into account when we look into building in an infrastructure. And then in some regions of the world, you may have triggers that will provoke or that will enhance the geohazard probability or risk, as well as climate change today, which are affecting a lot some of this region, in particular in tropical terrain. Or even in Switzerland, recently, this year, we had a very heavy snowfalls that provoked several road ruptures and even railway ruptures because of landslides. So now, when you are building an infrastructure, you absolutely need to take into account this potential event, this potential disasters. And there are people in the construction companies as well in the infrastructure operators that are dealing with that kind of stuff. And these are the geotechnical engineers. So they are dealing with the mitigation of these events, but they are also dealing with the monitoring of the risk of these events. And they are using conventional technologies like inclinometers, strain gauges. They may also use remote sensing, but they can also use optical fiber sensors, as we will see in this presentation. Well, so this is all about geohazards, all about a little bit of optical fiber, and now we will deal more with optical fiber. We'll talk about actually what's the physics behind the instrumentation, what's the physics behind the measurement principle. So a distributed sensing system using an optical fiber is a system that turns an optical fiber into a continuous sensor. It is not, or you shouldn't understand that we have an optical fiber that transports the signals to make measurements and that we have point sensors connected to the fibers. No, it's the whole fiber itself that is a sensor, a continuous sensor. So we have a continuous thermometer, a continuous strain gauge that can be laid along a structure like a pipeline, a road, or a waterway, a railway, just name it. So distributed sensing is turning an optical fiber into a continuous sensor by measuring changes in properties in the optical light, in the light transported by the fiber. And that's possible through one physical phenomenon known as light scattering. So here is the physics. And here in this graph, in this picture, actually, you can see the propagation, or a representation of what's the propagation of light in an optical fiber. And you have the light that is captured by the optical guide. And you also have a representation of light scattering. Usually light scattering is a phenomenon that will come from the interaction of a light wave with a change in density in the medium. So the denser the material where the fiber propagates, well, the higher the probability to have scattering we have. So that's what we are observing here. So if we have a change in density, we have scattering. And if we analyze, we look if we look at the light that is propagating in a fiber, for instance, and that we have scattering, and we are analyzing the spectrum of the scattered light, we will observe several peaks. There is one, and each peak is at a distinct color. The one that is of interest to us is Brillouin scattering, because it has the sensitivity to temperature and strain. So actually, by monitoring the change in color of the scattered light, we can tell that we have a change in temperature, a change in strain on the fiber. So we have we know that there is a thermal stress or a mechanical stress on the optical fiber. So that's the phenomenon on which we rely to achieve the sensing operation. So how does the sensitivity of Brillouin scattering with temperature work? Actually, we have here an example of three Brillouin peaks measured at three distinct temperatures. And it's varying from -25 degrees C to 90 degrees C. And if we report the peak temperature, the peak frequency for each spectrum on a graphical representation, like we have on the right, so we have a relationship between the peak frequency and the temperature. We see that the relationship is linear, and that's a common behavior for all optical fibers. It's the linear relationship between the scattered light peak frequency and the temperature of the fiber. So we have a linear sensor. Now, such relationship between temperature and Brillouin frequency is also valid for strain. So we can have, or deformation. So we have here a representation of the graphical, we have a graphical representation of the relationship between the applied deformation and the measured frequency of the optical fiber, in the optical fiber. So in both cases, we have a linear sensor, we have a linear strain gauge, and we have a linear thermometer. And well, actually, that's how it works to measure strain and temperature, but it doesn't tell us how we do distributed sensing measurement. So the distributed sensing operation is achieved by using the very same concept as the one that is implemented in radar. In radar, we have an an electromagnetic pulse that's propagating down the air. And as soon as you have an object, part of the signal of the pulse is reflected, and by measuring the time of flight of the pulse back and forth, we can get the localization of the event. So that's how the measurement or let's say the localization is achieved in an optical fiber, and how we can spot events all along the fiber. So what we do actually in the optical fiber is inject an optical pulse into an optical fiber. We gather all the pulse coming back. By doing a time domain analysis, we can locate all these events, all the events, yes. And by doing a frequency domain analysis, we can extract the strain and temperature information. So we combine two analyses, or we can say that we combine two instruments in one. One is like an oscilloscope, and the other one is like a spectrometer or a frequency analyzer. And we can get the information about strain and temperature. So the measurement in that case will look like a three-dimensional spectrum. We have intensity, we have frequency as a function of frequency, and distance. And if the temperature, the fiber temperature or strain is constant, is uniform, all the peak that are the result of the scattering, all the peaks are aligned. So we have the very same Brillouin frequency. Now, if I create a hotspot, I will see a new peak of the line, of the alignment, and I will lose one peak in the alignment. And by determining all the frequencies, all the peak frequencies, I have what we call a temperature profile. Here, for instance, we have the example of a temperature profile, which is measured along a pipeline crossing the Andes. And well, the representation here is a bit anecdotic, but it's interesting to see how sensitive the technology is and how it can show or evidence the environment signature. So for instance, here we have the temperature evolution along 30 kilometers of the pipeline. And in parallel, you can see the altimetric profile. So the change in altitude with distance. So the temperature is just the inverse of the curve of the altimetric curve. And that's not a surprise, because the higher you go, the lower the temperature. Now, the measurement performance of such technology is very important, because it's nice to measure temperature along tens of kilometers, but if your resolution is 10 or 20 degrees or 1,000 microstrain, you may not capture the right event. You may not be able to spot a geohazard risk. So the idea is to use the instrumentation and make sure that it has the appropriate performance. So today, we are working on the elaboration of a standard within the International Electrotechnical Commission for distributed temperature sensors and distributed strain sensor. And if we apply the methodology to analyze the measurement performance, we can see that the repeatability over 50 kilometers of sensors, or let's say 50 kilometers of a transport infrastructure, can be as small as 1 degree at 50 kilometers or 20 microstrain, using a 2-meter spatial resolution and averaging the measurement over 10 minutes. Well, the spatial resolution is somehow the maximum, the size of the event that we can detect. Now, if we need to detect or to measure smaller events, then we need to work with smaller spatial resolution. So actually smaller pulses. So then the performance will change, and we may have to degrade a little bit or accept a degradation in the measurement performance or increase the measurement time. But at least we will be able to see smaller events, or to actually measure with a rated performance smaller events. Well, this is a little bit or those two graphs show or illustrate what the interdependence of the various parameters of a distributed sensing system. So we have to deal with the fiber attenuation, splices, connectors, and that will affect the measurement range. And we can manage longer distances by using longer pulses or improving or increasing the averaging time. But there is really an interrelationship, there is a relationship between all those three parameters. You cannot have a 50-kilometer measurement with a 0.1 degree C and 10 centimeter spatial resolution. That's not true. That's impossible. Now, if your infrastructure is very long, you may use optical fiber amplifiers like EDFAs. And that's kind of standard in telecommunication. And what we have done recently is implement, for cases where you cannot install an instrument in an intermediary station, we have used optical fibers, and we have developed an approach to increase the measurement range up to 300 kilometers, while we are keeping the measurement performance at 2 Kelvin, or well, actually 2 degrees C. It's about the same. And here we have well, the measurement uncertainty. So in some cases, this is the solution where no instrument can be installed in the middle of nowhere. Well, no, we have been talking about the instrumentation, but of course, well, you need a cable, you need a sensor, and that's a key element. A sensor must be robust. A sensor must be sensitive. The sensor must survive its environment, and it must be, in most of the cases, laid in the ground. So if we look at telecom cable, they are perfect, or very good telecom cable are perfect temperature sensors, because they are designed to isolate the optical fibers mechanically. And usually they are built according to standards and to the electrotechnical committee, the International Electrotechnical Commission standards, so that, well, the characteristics, the mechanical characteristics of these cables allow them to operate and survive difficult terrain, difficult environment. Well, I just say that, well, for a telecommunication cable is a perfect temperature sensor, but that would be a very poor strain sensor, for the very simple reason that the cable is designed, the telecom cable is designed to isolate the optical fiber mechanically. And that's not what we want in a strain sensor. We want to make sure that the temperature, that the optical fiber will see any deformation, any mechanical deformation on the cable caused, for instance, by a landslide. So this is a kind of complex operation, but we succeeded in partnership with several cable manufacturers to develop sensing cables that are strong enough to survive the environment, but that are sensitive enough to capture strain. And that's why those cables must also follow the standards from the International Electrotechnical Commission. Now, you may also work with hybrid cable where all the functionalities for strain and temperature sensing are combined, and as well telecommunication. So then in that kind of cable, you will need sensing elements that are mechanically isolated for temperature sensing, and other elements that are sensitive to strain. So this is currently being used, or this is more recent and being implemented in few projects all over the world. Well, so enough of optical fibers, and just get back. I think it's time to get back to geohazards. And if I'm getting or following my categorization of geohazards, erosion, subsidence, and landslides, we will see how they may look like when they are measured with an optical fiber sensor. So there's three categories, and there's three types of events can be detected by using strain and temperature measurements. When I'm looking at erosion, I will try to detect a change in soil temperature. When I'm looking at a landslide, I will try to see or to detect a change in strain in the ground, and the same for subsidence. And if we look at it more specifically through examples, here we have a pipeline right of way where a landslide was detected. You can see here on the bottom right the strain profile, and you can see the strain profile development over time caused by the landslide. And on the top, you can see the development of the landslide over time. You see the peak development, the peak change evolution with time, as well as, well, how the section that is before or after the landslide is quiet. And that's interesting because with a distributed sensor, we can determine what's the transition zone between the quiet region and the landslide. So we can determine the interface between the moving ground and the stable ground. And we can also determine what is the speed of the landslide, so that people know if it's time to take an action, to move, to go on the field, and conduct protection works. Well, such behavior can be also observed in subsidence. Here we have an example. It's not a pipeline. It's a project in Mexico where we measured, we tested the soil subsidence detection capability of the technology. So we embedded optical fibers in the ground. We loaded the soil with some material, the soil on top of the pipeline, and we can see the strain profile here in green, where we have a succession of compression, of tension, compression, and again tension, which is kind of typical of such event. So that can be, let's say, confirmed by numerical modeling and all the theory of soil displacement. And we were able also to extract the settlement of the soil. So what was the vertical motion of the ground caused by the load. So the system can also detect subsidence or monitor subsidence. And looking at erosion, so for erosion, the idea is to detect a temperature change. Here we are back to pipeline. It's a pipeline in Mexico again. So we observed a temperature drop over time, and it gets back to its original value. It was very localized, as you can see on the bottom right. And actually, the temperature drop was caused by a heavy rainfall that infiltrated into the ground and, let's say, enhanced the hole that was present in the pipeline ground and provoked further expanded the hole. And actually, we had an enhancement of the erosion phenomenon. So that's the kind of event that can be detected by the system. Okay, so we have reviewed the three type of events and the three categories. We have seen how they can be characterized by a ground movement, by a distributed sensor. So we have their signature. So now let's go to some more information. And here we are going to talk about what is the installation. So some cases. So for instance, for pipeline, when you can install the cable at the same time as you are building the pipeline, you can lay the optical fiber for temperature sensing and telecommunication on top of the pipeline for leak detection if it's a gas pipeline, and lay the strain sensor on the right to capture to eventually capture soil movements such as landslides. And in reality, it looks like here. So on the top, on the right picture, you can see the installation of the optical fiber directly in the trench during the construction phase. If you want to monitor the status of the soil along a road, you can just build a trench or excavate a trench in parallel to the road on the side and lay the optical fiber. But you can also embed directly the sensor into the ground, into the pavement, as it is shown here. When you don't have other options, as it is the case here, and the fiber optic cable was laid in the road because it was in a village in Switzerland, in St. Moritz. And but that also allows you to detect a deformation in the road and spot all the risk for the road. So here the idea is really to detect crack formation and the degradation of the road pavement that can lead to a rupture by a landslide. Embedding sensors into structures, that can be done also along a waterway, like here, so in the embankment, and several trials were conducted to see what was the best position to detect seepage, but also prevent a collapse of the ground movement of the embankment. So here we combine temperature sensing for seepage and strain sensing for the embankment collapse. Well, now talking about the optical fiber, talking about the geohazards, we have instrumentation that can detect ground movement. We have instrumentation that can identify ground movement, but usually you don't expect an operator to sit in front of an instrument screen waiting for an event to happen. So that's not acceptable, and it's not really economical. So what you want is something unattended, automated. So that's why we have geotechnical monitoring system, where we have a layer doing all the measuring, extracting the temperature information, extracting the strain information. All that information is sent to a monitoring station or server that will analyze any change in temperature and change in strain, and as soon as an abnormal behavior is detected, generate an alarm. And then from there, an engineer, a geotechnical engineer, a control room operator can connect and analyze the data, explore why, and try to understand why we had this event coming up. And then you can export data and in the form of, let's say, text file, ASCII file, and do your own simulation when you are a geotechnical engineer. And the best way to display the information in a linear structure is to use maps, like in a geographical information system, and that's how it is usually implemented. So you have the infrastructure that is being monitored. You may have events that are popping up on the infrastructure. You can zoom in and view what's the status, what is the location, the coordinates, the actual position, and the severity, and of course the occurrence. And then if you want to understand why the alarm came up, then you can open another window showing the temperature evolution over time for that specific section, so that you can analyze the behavior, and you can do the same for strain. You can also look into the strain and temperature profile, and then compare data over a long or certain period of time, and trend the behavior and understand better what's happening, and eventually take a decision. Shall we go on the field? No, that's not a big deal. It's always human decision, but at least you have the ability to double check the alarms and also use the data for further analysis. Well, so that's how a geotechnical monitoring system can be implemented, and it is actually being used in several infrastructures. And I would like to discuss only one, which is probably an emblematic case. It's a pipeline crossing the Andes. So for those of you that are not familiar with optical, with the gas production in Peru, you must know that actually all the gas fields are located in the jungle in the eastern part of the country, and most of the people live on the coast. So you have to cross the Andes, and crossing the Andes is a challenge. It's a challenge because we have a mountain range with steep slope, high peaks, deep valleys, canyons. But that's not the only difficulty. It's also a tropical climate, so heavy rainfall during the summer. And just to make the situation a little bit more interesting, you have seismic activity. So that's a kind of cocktail that doesn't invite you for building pipeline. But anyway, if people need gas, you have to do so. So and that's an example of the pipeline right of way of the first kilometer. So in the most critical part of the pipeline, the operator decided to install monitoring systems, and well, in their great wisdom, they selected an optical fiber. They selected optical fiber sensing, so a geotechnical monitoring system, and 60 kilometers were implemented. And since the beginning of the operation of the pipeline in 2010, several events were detected. And among the first, we have erosion. So actually here you can see a cold spot that was generated by water infiltration, and have a drop in temperature. And so we had crack formation in the pipeline right of way, heavy rainfall, water infiltration, and then the beginning of erosion that could expose the pipeline on the long term. So that was an important event to detect. Another kind of event that can be, or that was detected soon after the pipeline started to operate, was a kind of a landslide. It's more like a rock fall, but we will put it in the categorization of landslide, the landslide category. And here we see that there is, over time, a change, a very fast and rapid change in strain. So because the rock had fallen, and we had a very defined strain profile, as you can see here. So the fact that we detect the rockfall is a bit anecdotic, because detecting a rockfall is something, if it doesn't stress the pipeline, doesn't matter. But here, because it was directly on the right of way, we detected the rockfall, but also the permanent deformation that was induced in the ground by the load caused by the rocks. So actually, it induced cracks in the right of way, and could have been a trigger for a landslide when the soil is saturated with water. Other event that was detected in about a year after the installation, after the beginning of the operation, was a landslide. So as you can see, you have here the development of the landslide. So we can detect quite early the landslide. We have a very small behavior here in January, and then end of February, we have a very large movement. We have a very large strain detected. So the system is so sensitive, and the technology is so sensitive, that it can be used really to prevent the landslide and take preventive actions to avoid a pipeline break. And of course, the preventive action means building containing walls, as you can see here. Well, so these are three examples of events that were detected along that pipeline, but there are other pipelines where events were detected, and including in this pipeline as well. And let's say, as soon as you have an optical fiber sensor laid in the ground, then you start to see how the ground is moving, and you can really prevent many events. Well, so now we have here, okay, so that's last comment leads us to the conclusion, and I can say that the technology is mature, and it has been implemented for over 15 years now. In terms of instrumentation, there are several instruments that can be used. Cables were developed to be installed and survive the environment. Some cables were implemented or developed specifically for a kind of environment. Those systems were installed for geotechnical monitoring, but also for structural health monitoring. I didn't mention a little bit about it, but you can have such technology monitoring bridges, tunnels. But that's probably that will be probably another webinar, because there is a lot to say about it. And actually, there are still challenges, because the cable selection is key. When you want to install a monitoring solution, you need to think about the application. What do I need to measure? What do I need to detect? Will I have to detect a landslide, subsidence, erosion, all three, or just subsidence and erosion? We don't need the same cable. In addition, the environment may have a strong influence on the cable selection. Because if I have rocky ground, so like in a mountain area, well, I don't want a soft cable. So I need a very heavy duty cable. So probably a cable with many reinforcing elements. Now, if I have a flatland with, let's say, sand, or let's say, well, why not a desert? In that case, well, we can just use a standard cable and we will be measuring a temperature change without being too much influenced by other events. So definitely it's the cable selection is key. And then we know the cable installation, the cable installation is also an element that needs a particular care. For instance, we need to make sure that the installation will not affect the performance of the cable, and that the installation will take care on how the cable will move in the trench. And the last point, which is not so much related to the sensing and the interaction between the soil and the cable, is the actual registration of the position. Very often this is neglected, but we have a distributed sensing. We can locate events, but we need references. And usually the cable length is not the same as the infrastructure, the transport infrastructure. So we absolutely need to take that into account. So there must be a very strong attention on the procedure that is being used. So I would like to thank you all for your attention, and I will be happy to answer to your questions. And well, if you want to know more, just visit our website or just visit my personal page. There's much more about this application. Thank you very much for listening.
Thank you, Fabien, for a very informative discussion. If you have a question, you can use the text box to the right on your screen and send something our way, and I'll be happy to pass that on. A couple questions that we have already is, first, one question came in is, how do you distinguish between strain and temperature?
Well, that's a very important question, and actually the distinction between strain and temperature is done by selecting an appropriate optical fiber cable. So when you select a telecom cable, which is in theory where the fibers are in theory mechanically isolated, and if the cable is good, you shouldn't see strain. So then you have a clean temperature measurement. But of course, if you want to do strain measurement, it's difficult to separate strain from temperature. So you absolutely need a compensation of temperature on the strain measurement. So you will use two cables, and because we by the nature of the geotechnical monitoring, you have to measure temperature as well. It's just natural to have both cables. Now, you may not need temperature compensation when you are talking about very large movement and when the temperature change is very small compared to the movement.
That's very helpful. Next question is really an installation-related question, and it has to do with the performance of strain detection cable. Is it reduced as if it's installed within a conduit?
Well, of course, because the conduit will isolate mechanically the optical fiber cable. So at the end of the day, if the ground movement is very large, yes, we will start detect. We start measure strain, but that's probably too late for the transport infrastructure we want to monitor.
Got it. And then another question related is how easy is it to fix cable if it's damaged?
Oh, that's very standard. It's actually the only thing that you can apply to optical fiber communication cable is applicable to a geotechnical monitoring system using optical fiber cables. There is nothing very different. So you only need to have trained people to deal with optical fibers and the right equipment. So an OTD, an optical time domain reflectometer for testing the quality of the cable and of all the splicing and the connectors, and you need a splicing machine. But most important is to have the right people. But it's exactly the same as what you need for a communication system.
Got it. And how do you detect a crack of a few sort of small millimeters when you measure with a spatial resolution of, say, 1 meter? So I guess the idea is getting a handle on the ability of the system to detect, very refined, small events.
Sure. I would say, well, from my experience, in all the projects we have been dealing with for now more than 10 years, that does not apply too much to geotechnical monitoring system, but it's more critical for structural health monitoring applications. Here that's key. Then in that case, if you use a time resolve technique as the one I've been discussing here, there are ways by doing post-processing to extract the information, and that has been quite successful because there is a bridge in Sweden. It's in Gothenburg, where a kilometer, it's roughly a kilometer of bridge, is being monitored with optical fiber sensors using a time resolve technique as ours, and using the post-processing we have developed for crack detection. So you can do that using a time resolve technique with 1 meter spatial resolution and a post-processing. So the post-processing would mean that we will look into the spectrum, the Brillouin spectrum. So we are back to the physics. If you have a problem, go back to the physics and it will be solved.
Okay, and if you have existing fiber that's already in place, the question is, how does sensing applications work with these older and potentially degraded single mode fiber?
Well, I probably should ask the question first: is your environment really, or is the environment really a risk for your infrastructure? If it's the case, then we must find a solution. If it's the case, well, we can use and I guess these are telecommunication fibers. So these telecommunication fibers can be used for temperature sensing, of course. Then, if these fibers are stressed, that means that there is ground movement, but probably is very large already, and we will detect it. Now, if you want to do a retrofit, that's possible. You use the communication fiber to achieve, or you use the communication fiber to transport your signal to the location where you think you have a movement, or by your experience, you know that there is a movement, a ground movement, and you can connect the telecom fiber to a strain sensing cable and monitor more specifically that section. So it's possible. We have done it as well. So you can have let's say a railway, because I'm always talking about pipeline, but you can have a railway with optical fibers laid for communication along the railway, and it's crossing some hilly region, and you want to detect landslides. Then you just open a trench, you dig a hole in the ground, you cut the fiber, splice a strain sensing fiber, you splice back all the fibers from the telecom cable, or you go just to the nearest strain, to the nearest junction box, and you lay your optical fiber, your strain sensing cable, and then you have your sensing system, or you have your old communication fiber system that is upgraded with a strain sensing system and strain and temperature sensing system. But that has been done in the past.
Yeah, and let me do a couple of quick questions before we conclude. Do you have any experience with geoformations caused by, or deformations caused by coal mines?
Sorry, I didn't catch the last word.
Do you have experience with geodeformations caused by coal mines? I'm not quite sure.
Oh, yes, yeah. Okay, coal mines. Yeah, so then here we are talking about subsidence, I guess. So let's say you have coal mines, and you have buildings built on top of in that region, and because you have subsidence, you have cracks in the houses, not to talk about, or in the roads, and we never did it, but I would be happy to help doing it. That seems a very interesting application.
And next one, is it possible to differentiate between horizontal movement from vertical deflections?
So that's, with a single fiber, that would be complicated. So you absolutely need, if you want to have a complete direction, if you want to measure the displacement, you want to measure the if you have more components in the soil movement, then you probably will need more than a fiber that are directed, that are really directed. Like you need, let's say, a two coordinate system to extract that information, basically. So you would need two fibers, one laid, and the two fibers should be perpendicular. So but that's possible. If you have a landslide, for instance, you can create a mesh of optical fibers and capture the whole displacement. So you can measure the amplitude of the displacement, the direction, and extract both directions. People are also talking about, not talking, they have done it. You can also use a geotextile to see how the ground movement is displacing. So, and the geotextile is equipped with several optical fiber, with a grid of optical fibers, actually. So that could be an option.
Good, thank you. We're coming up to the very end of the hour, so I think I'll stop things there. I will say that Fabien has his email there, so if you've got other specific questions, you certainly can access him that way. This entire presentation will be loaded fairly quickly on the FOSA website, so you can access it again. And just as a reminder, next month we will have another presentation. This one will be, again, given the number of installation questions we have, it's probably timely, but we'll have Duraline, which is in that space, will be doing a presentation on their installation procedures. And that is on April 19th, also at 2 o'clock Eastern time. You can sign up on the FOSA website. Fabien, thank you very much for a very informative presentation. We really appreciate your sharing your knowledge with us. And that concludes our webinar.
Thank you.